It looks like this might work because I think we have ignition.
That'll work. I already clocked.
Hello and welcome back to Calculus1 on this almost glorious Saturday morning. I just want it to be Sunday. I want to teach every day. So Saturday morning, we are back in chapter 4, back in optimization. Let's do more problems and have fun. Now to recap what happened last time at some point, we said optimization is going to look for a min or a max, both, right? Well, one per problem. You want to have maximum area or minimum area or maximum volume. You know, you want to have one of those concepts, maybe maximum profit, minimum cost. So these are all applied problems. So we are looking for two numbers. In this case, this is a very first example just to illustrate how stuff works. So we have two numbers and we want them to add to 10. So if you have two numbers add to 10, we run into something that we call constraint equation. So we want to find numbers so that if they are to add to 10, this value is a max. And we obtain, so now we have the pair of equations, and the procedure we said is always the same. What we do with this is we take the value, first equation, we solve for x, plug in a second equation, and then differentiate. We know when we differentiate equations, we get, so that's done here. When you differentiate equation, you get this max value, which is some kind of number, becomes 0, which we know that derivative equal to 0 is the way to find critical points, which ultimately leads to min or a max. And then as we work this problem out, we came up with two values, and those two values were 20/3 and 10/3. So if you use these two numbers, you will maximize that product that we had, which was x squared times y. And then we did a whole bunch of dimension problems for rectangle, where we look for the area, the rectangle with the largest area, given the constraint equation of its perimeter. And those problems are famous as farmer problems, because farmer would have x amount of fence available, and then what is the maximum area that he can enclose. So modified farmer problems, we have a river there with perimeter 1900, let's say. Then we have the three bins, right, which would introduce 4 y's. Then we had this whatever shape rectangle inside the rectangle, and so on. So now we can work with other shapes other than rectangle, but we can also do some of the business applications. But let's take a look at few of those so that we can have variety. All right, so what else is cool? So I asked you all to take a piece of paper at home and make a box with the largest volume and bring that box here to class and show it off to everyone. Yeah, I did. I know. And the good thing is that everyone did it. So for those watching live, we have this wonderful colorful box here, which are all correct, and I'm very, very proud of that. So let's take a look at calculations you guys did again correctly to make these boxes correctly. So let's take a look at that. So what we have is a piece of paper that it's square.
I'll do it right now.
So you have a square piece of paper, and you want to make a box with no top, of max volume, right? So box with a max volume, no top. Let's say that the side of a paper is 10 inches. Side of the paper is 10 inches. So now how do we do this? Well, yes. Very good. So we are going to cut a square in each corner. You cut those squares out and you throw them away. And then you fold sides up on those dashed lines. Take pieces of tape and just tape the whole thing together. So it takes it's quick. Yeah, it's really quick to do this. So now we know that the entire length here is 10 and 10. And we see that this little piece that you are cutting out is x. We don't know how much we're cutting out. So volume of the box is x times y times z, right? If you have a box of any kind, it's x, y, and z. So now when you put your box together, when you take your box, you will see that what's the height of this box that you're going to get, looking at my diagram above? X, very good. And what would be, these two sides on the bottom are obviously the same, it's a square base. So what is the length of each one of the sides now? 10 minus 2x, very good. 10 minus 2x, because you see that you have a 10, right? Piece of paper is 10 by 10, and then you take 2 x's from each side. So each length of the box is 10 minus 2x. So now when you plug that in a volume formula, you have 10 minus 2x squared, because that's your x and your y, and then times x, because that's the z, that's the height. And you want that to be max. Observe that you only have one equation here. You have only one equation because... What the hell happened with the rest of them? You only have one equation. Everything is already in x, right? One variable. So we don't have to do much work. Okay, 10 squared is 100 times x is 100x. Minus 2040 x squared, and then plus 4x, right? Plus 4x cubed is equal to a max. That's when you FOIL, and then you take the derivative because you want to maximize, right? So this max becomes a 0, so derivative equals to 0. We have 100 minus 80x plus 12 x squared is equal to 0. And we can divide by 4, right? That's 3x squared minus 20x plus 25 is equal to 0. All right, so I just divided by 4 to reduce numbers as much as I can. So now to solve this quadratic equation, I have to get it off the... Yeah, anyway, let me just see. Is this working? Yep. Alright, so we use quadratic equation now. So negative b, so that's 20 plus minus square root of 20 squared is 400 minus 4ac, that's a 300, divided by 6, which is 20 plus minus 10 divided by 6, and then that's 30 divided by 6 is, well, we have two solutions. X equals to 30 divided by 6 is 5. And we also have 10 divided by 6, which is 10 divided by 6 is 5 thirds, right? I keep losing random writing that it's... Oh, it's trying to see. Okay, I know. I'll fix that later. All right, so now we have two answers. Which one do we keep? Which one do we throw away? We throw away the 5, yes. Why do we throw away the 5? Because if x is equal to 5 and you cut 5 from the left and you cut 5 from the right, right? You just throw away everything. So we have to throw that one away because it makes no sense. And we keep 5 thirds. So now you have 5 thirds, so side is going to be 10 minus 2 times 5 thirds, which is 10 thirds. So 10 minus 10 thirds is 20 thirds. So the box has dimensions of 20 thirds times 20 thirds times 5 thirds as a height. Inches. So if you use the paper, square paper that is 10 by 10 inches, you will have 20 thirds by 20 thirds by 5 thirds. So this type of calculation is important. Let's say packaging engineering, right? It's a whole branch of engineering that it's extremely important because goods have to be shipped, right? There's a whole family of problems with the least distance calculation. Problem number 20 and many others in the homework talk about find point P. On the curve y equal x squared that is closest to 18, 0. So we are looking to what's the ultimate objective of this problem? What are we trying to do?
Specific point.
The what? The least distance. So I have this x squared thing, and I have, now this is just x squared, so we know it lives on the right origin, and then you have a point 18, 0 somewhere, and we are trying to find this mysterious point where this distance d is what? Minimum. Exactly. So this is what we're doing. So dare I say clearly, we are supposed to use distance formula between 2 points. We have a known point 18, 0, and we have unknown point xy. So the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, and those are the x1 y1 and x2 y2 are coordinates of those 2 points. So the equation is square root of, and what do I have now? x2, so that's going to be x minus 18 squared plus y minus 0 squared, and that needs to be a minimum because I have 2 points. The 2 points that I'm using are x and y and 18 and 0. So here's your x2 y2 and x1 y1, and we just plug in. So now we have equation that is x minus 18 squared plus y squared is equal to a minimum, and that is our objective equation. We also have a constraint, right? Y equal x squared. So this is our pair. We work with these two equations to figure out the values for x and the y. So how do we do this? Well, you have what y is equal to. When you plug that in the other one, it becomes x to the fourth. Hit it with a derivative, which would be equal to 0, right? Mean becomes a 0. And then, so here, I'll give you, what, 22 seconds to finish this, and then I'll kick in. 3 seconds left. And time's up. Oh. So we are going to take the derivative. Now when you are taking the derivative, this square root is actually a half power. So we know we're going to get the derivative divided by the 2 times the square root. So the derivative of the inside is 4x cubed plus 2x minus 36 divided by 2 times the square root equals 0. I'm not going to bother writing the square root in because look, when we cross multiply it dies, right? So this equation that seems awful is actually very easy. Divide the top equation by 2, right? You get 2x cubed plus x minus 18 equals to 0. Well, now that's an issue, right? Because this is not, yes, became x to the 4th when we plug in, right? Because you have y is equal to x squared squared is x to the 4th. So that's the last term before minimum, before equal sign, I mean. So now we have to solve this somehow. And why I say somehow? Because it's bad. Now the way we solve this one is we call Mathematica to help us. So sometimes you are able to factor, right? Sometimes you can use quadratic equation. Well, this is a cubic. And solving cubics, if you can't factor, is really crazy because the formulas are insanely complicated. So what we do is we go Mathematica. You all have this on your email, right? The famous $1,000 gift. So make sure you install this and use it. It's very easy to use. Just use the Wolfram Alpha query and talk to it. Solve. There's an S. No. Solve 2x cubed plus what?
Yeah, it's simple.
X minus 18 equal to 0. And you hit enter and then you wait. And then it tells you that the solution is x equals, you have 2 complex solutions and x equals 2. We keep x equals to 2.
Like apparently Eli's radiated over something, so he will be later than normal.
I will, okay. So I'm just going to state this for the record that I feel extremely lucky that nothing happened to my car today. And you should too, because we have 2 car issues for the day. Yeah. So that was Mathematica. Or whatever other kind of witchcraft you know. I don't know. Whatever works for you.
Can you do that thing where like, I forget what it's called, but like you
Oh, from Pre-Calc1? Yeah.
do that.
You can do it.
You just guess, but like.
Yes. So now we have x equals to 2 and y is x squared, which means 2 squared, which is 4. So the point P we are looking for is 2, 4. That's the closest, right, point that it's point on the XY that it's closest to 18, 0. Yes.
To get that, you just plugged it into mathematics, right? I wasn't looking.
Yes.
That's something in mind.
Here is, yeah. Great. That's that problem. How about we talk some money, cost analysis, and that kind of stuff, because some of you might use this to make some serious income. Yeah. Let's see. Let's make a scenario, make up some numbers, see how it goes. So let this be a shore where you have, ground shore, right? So you have the soil on the left and the sea on the, so soil on the left and sea on the right.
Some waves.
I could put waves, but they're gonna get in a way of drawing. Here, waves. There's your waves. We are going to have an oil rig very close to the shore, a few miles.
That's safe.
Don't worry about regulations.
This is a money problem, not
We
a
have-
humanitarian problem.
We have a different type of a government now. So we have an oil rig. We'll call that OR, oil rig. Or, and then we have a refinery right here, oil refinery. We'll call that OR. So, refinery processes the raw oil into products that we use, like plastic, amongst other things. So now we have choices. This is close, few miles. So we don't want to, get all of this loaded onto a tanker and then just go. We can build a pipeline, right, directly to the oil rig because it's so damn close. 1 mile on ground. How much could it cost to build a pipeline 1 mile on the ground? Let's put some number down.
20,000. That's pretty cheap, actually.
Yeah, that is pretty cheap. Some usually 100,000 for 1 mile.
That's fine.
So $100,000 for 1 mile. And 1 mile underwater?
250,000.
I like it. 250,000 underwater. We have choices. We have a choice to run on the ground as much as we can, and then the shortest distance to the oil refinery, right?
Mm-hmm.
So if you take a look, this ground line, that's the cheap pipes, and then you also have the cheap, right? But then you can say, maybe I can just go straight through this way. I have nothing on the ground, but this is the shortest possible distance we can actually have, right? So these are the two choices. Now let's see, how far is this oil rig? How far out?
5 miles.
5 miles it is, thank you. And how much north? Because 10 miles, okay. And the reason why, those are the things we can measure easily, right? So as you can see, everything that we have there is stuff that you measure easily. You can just drive up, right, back to next to the pipeline, you went 10 miles, and you can take a boat 5 miles to drop off workers to the oil rig. So there you go. We know the distances. Now, Pythagorean theorem will also tell us the distance here, which is 10 squared plus 5 squared, which is 100 square root of 125, which is 11 point blah, right? So square root of 125. So 11.18 miles is the hypotenuse on this triangle. Well, let's call. So, you know, I'm going to change the color of this line into a blue line because it's completely underwater. So I'm going to have a choice 1, which is going to be the black line, and the choice 2, which is the blue line. Okay? So let's calculate the cost for choice 1, which is the black line. Choice 1. So I have 10 miles for 100,000 plus 5 miles for 250. So that's 1 million plus 1.25 million, and we get 225 million to build a pipeline this way. So $225 million to build a pipeline to use the black path, right, which is you go up on the ground using the cheapest possible path, so as much as you can, and then using the shortest possible way, right, to get into the refinery, which means you're using the least amount of the expensive pipes. Choice 2 is blue. And that's clearly all underwater. We have 1.18 miles to go, but it's all expensive piping. And that's going to be 11.08.
11.18.
That's what I said, please pay attention. Times 250,000 to be 2 million, and then so 2.795. So we see that the option to go with the on the black route is $500,000 cheaper, right? Now $500,000, that's a considerable savings. And then you show up, say, I took Nick's Calc1, I can do better, right? I can go up the shore for some distance and then, right, like this, and then go to refinery for the option 3. I want to optimize, right? I want to optimize this route and get the cost to be minimal. So now we are going to try and make the cost to be minimal. Now clearly over here I have this distance x, which I don't know how far I have to go in terms of the ground pipe. And I also have the red d, which is the distance underwater, which is again something I don't know. So let's see our choice 3 equation. So choice 3, what we are minimizing is the amount that we go on ground, which is x times 100,000. So that's 100,000x plus 250,000 for underwater, which is d, and we want that to be minimum. Fine. I have to figure out everything else. So would you agree that this distance here, dash distance, is 10 minus x. Awesome. So now you see a relationship in a triangle. You see the triangle, right triangle up there?
Yes.
So you have a right triangle up there that connects d and x. That will be your constraint.
Yes.
And you already have objective function. So 10 minus x squared, which is one of the legs, plus 5 squared is equal to distance squared. So now you can work that out and then plug into the other equation. So that's 100 minus 2x plus x squared plus 25 is equal to d squared, from where d is equal to the square root of, and then you have what? 125 minus 2x plus x squared. We plug that in our equation. So this is how, what you call real life, because clearly over here is not real life, you know. So you just plug this in now. We have 100,000 x plus 250,000 times the square root of 125 minus 2x plus x squared equals to a minimum. And I hope you see that the entire equation is in terms of x. We hit this with the derivative and solve.
You can do it the other way, correct?
What is the other way?
You can figure out what d is.
Yes, you can solve x equals to, yeah. I mean, you will have to, once you find x, you will have to utilize the equation to figure out d as well. All right, so let's see if we can take this derivative. It works out to be 100,000 plus 250,000. The derivative over here is 2, that's square root, and then on top I have the derivative of this, which is 2x minus 2. Now we can't equal to 0. We can't drop the square root now because we have this plus 100,000 on the other end. So we have to keep that. Now these 2's will cancel. So I have 250,000 x minus 1 divided by the square root is equal to negative 100,000. So I move 100,000 to the right. I cancel those 2's. And this is what we have. And now what I'm going to do is move the square root to the right and then square both sides. So I have 250,000 x minus 1 is equal to negative 100,000 times the square root of x squared minus 2x plus 125. And I will square both sides. So there is a square on this side, square on this side, and that kills the negative. So when I square, 25 squared is 625, and then we double up zeros, so now there's going to be 8 zeros, times 10 to the 8, x minus 1 squared, equals to, this at 5 zeros, so 10 to the 10. The negative becomes a positive. And square root dies, so it's x squared minus 2x plus 125. Now look, divide both sides by 10 to the 8. It becomes 625 x minus 1 squared is equal to 100 times x squared minus 2x plus 125. Divide into 6.25 times x squared minus 2x plus 1 equals to x squared minus 2x plus 125. This is just annoying calculations, but we do it. So 6.25x squared minus 12.5 x plus 6.25 is equal to x squared minus 2x plus 125. And we put this together. And we get what? We get 5.25x squared minus 10.5x and then minus, is that true? 118.75 equal to 0, I think. Now, quadratic equation will obviously not happen because I have Mathematica. Well, you know.
You're not gonna give us like problems like this in the past, right? Like ones that like we can't factor here.
Possibly.
Will it be like a trick we need more?
Yeah, called Mathematica.
Oh.
So 525. We go again with solve 5.25 x squared. What is the rest? Minus? Minus what? Did anyone take no? How much? So it's 525x squared minus what?
10.5.
10.5x 75 equal to 0. Enter. And that will give me two values. Now observe that I'm going to use the approximate form because I want decimals. Observe that one number is negative. Well, we can't use negative x as a distance, so throw that in the garbage. And use 5.86. So 5.86 miles. So we will have to run pipe on the ground for 5.86 miles and the rest is underwater to minimize the cost. So now when I plug all of this in, the answer better be smaller than any of the previous two, otherwise I'll explode. So now we have to find d, square root of 125 minus 2 times 5.86 plus 5.86 squared. So we compute this now. So square root of 125 minus 2 times 5.86 plus 5.86 squared. I get 12.15 miles. So what's the cost? Cost 3 would be $100,000 times 5.86, that's on the ground, plus $250,000 times 12.15 miles. Well, the first number is easy, right? You just move the decimal. And I get 3,600,000, which makes no sense. Which means that there is some major mistake somewhere along the line. Do what? Yeah.
No, that's true.
Yeah, because it didn't make sense when you got 12.15.
Yeah, for real.
It's gotta be a lot smaller. Did you square root it?
one you just plug it in, it's like 147 something.
Well, let me see. I'll use the calculator. So the square root of 125 minus 2 times 6 plus I still get 12.15.
It's not supposed to be 12.15, right?
Yeah, because I just.
It can't be. Yeah, exactly. It can't be. Something is seriously wrong.
Really mess up that.
There's no way, because as you can see, the blue line is 11.18
Yeah.
and the other one is 5, so it has to be in between. Something is wrong. Something is seriously wrong. There is calculation error somewhere which produces these numbers that make no sense. I'm not sure where it is, but it's somewhere. This number has to be smaller than both of these. It has to be smaller than 2.25 million. Has to be smaller.
So when you leave things at the top here.
Well, I'm trying to see. So now we have, that's 100 minus 2. Ah.
Right from the beginning?
Right at the beginning, yes. You see this term over here?
Yes.
That's negative 20x.
Yeah.
Okay?
Yeah.
And once that becomes negative 20x, the rest of the problem will change accordingly.
So let's do it again.
Do it again.
Might as well get some practice.
So that needs to be 20, which makes this 20, which makes this 20.
Makes 2x minus.
Which means this 20, and which makes
2x minus 20.
2x minus 20,
Then x
which
minus 10.
which makes this x minus 10. So we have to change
Everything.
It's not a big deal. I mean, you know, it's terrible. So that's gonna be a 10 over there and 20 over here. So now, as I expand, this is different. This is 20, right?
Yeah.
And this is 100. And this is still 20 on this side. And I'm just going to pick up from here and change everything else. So that was 20. Awesome. So what do I have? I have 12 point. This was 12.5, so it's 125 x plus 625 is equal to x squared minus 20x plus 125. So that's 525 minus 105 x plus 500 equal to 0. We can divide by 5 because, as you can see, all the numbers line up nicely for that. That's gonna be 1.05 x squared minus 21x plus 100 equal to 0, and that's our new equation that we are going to plug into Mathematica and hopefully get a better, well, not definitely get a better solution. But this time, so 125 squared, this needs to be 21, and this needs to be 100.
Then you have 1.05 too, right?
Oh, 1.05, you're right. And it just made it much worse. Oh,
Why?
because I got x equals 0.3 miles. Okay, look for mistake. Find a mistake while I eat the donut.
Not your day today.
Yeah, is there any more?
What the hell?
April Fool's Day, what is
Yeah. April Fools. Okay, Brian's gonna fix it.
it? What? No.
Is that why you? Oh, you came up for it. What the hell? We just fixed it.
You just made it worse.
So this is how I'm going to solve this issue. Delete page now. Solve. $250,000 times x minus 10 equals to negative 100,000 times the square root of x squared minus 20x
You have a square root there.
125, yeah, to the 0.5, and then just eat. $7.82.
See that one.
Mm-hmm. So this is what you're gonna do. I mean, what are you gonna do tomorrow all day? Right? It's Sunday. So you go and you grind through this algebra to get 7.82 miles.
Yes, we will.
I have work.
I'm sorry?
I have work.
Yeah.
No, from like 10:30 to like 8 o'clock.
Yeah, this.
What are you gonna do up to 10:30? And then after 8, you can do half before and half after.
Well, before I wake up at like 8 o'clock.
Wake up at 6.
Applebee's? Well, that's my first job. That's my.
Oh, you were the one with you.
Yeah.
All right, D.
Yeah, I was gonna say.
Square root of 125 minus, that was 20 times, right?
Yes.
7.82 plus 7.82
Square.
squared. Let's see if we can get this value now.
I think it's gonna be big too, though.
We don't know that yet. Let's say. $5.45.
That makes sense. What do you say?
So finally, cost for the third case.
It's like the fourth time.
So cost for the third case for the fourth time is 100,000 times 7.82 plus 250,000 times 5.45. That would be drum roll. What happened with drum roll?
You got 2 beats.
Well, it's
And here we go. 2,144,500. Oh yeah. So here we saw 225 million. It was the cheapest one. 2,250,000. 2,144,500. So that's 500. That's a 9. It's a 5. That's a 0. It's a 1. So this calculation saves $105,000. Do you see how easy for companies to give you, like $10,000 for this calculation as peanuts for them? They save 100,000 on it. They give you 10,000 for this calculation. You do this in 2 hours.
no, you give them 30,000. I want 30,000.
You want 30,000?
See, I'll do it for 25,000.
There we go. We're talking business now. So business applications for this are huge. Think about how many of these problems need to be done on a regular basis. And these are types of calculations that you do. Now, why does it go so bad so many times? Because we are dealing with numbers. This is, reality. You will never deal with x squared plus 3 when you start working somewhere. And you'll never deal with numbers 2 and 5, and because simply not like that. You deal with decimals, you deal with, right? And you also see that optimization works in this case, right? We did get a number that is smaller than either one, and what we did is we optimized the path. So if you use the, somehow you want to believe that either black or a blue path are the cheapest ones, because the blue is the shortest distance, right? But the blue pipe is expensive. And then you have the black, on the black path, you keep the cheapest pipe for as long as possible, so that you can run the expensive for as short as possible. That works to be more expensive than this kind of mid-run. So from the blue choice, right, which might be for some people the most obvious one because the shortest distance, you save $600,000, over $600,000. So that's a huge saving, right? So that's one of the business application problems. Yes.
We should calculate the rate of flow in each pipe.
I'm going to leave that for your project,
Nice.
so you have something to enjoy in life.
Oh, man. I should just leave
And
this out.
I mean, there are a whole bunch of other problems that you can enjoy. If you really want a challenge in life, you can try problem 49. Spend a few days on it, see how it works. I actually worked out myself problem 47 when I was installing my theater, so that's a nice, useful problem to work on. Whole bunch of I just seen a problem that says blood testing. Suppose that the blood test for a disease is given to a population of n people where n is large. At most 10 individual blood tests must be done. The following strategy reduces the number of tests. That's interesting. They give you an equation too, so not as crazy. Problem 29 is also one of the more frequent problems. You might want to look into that one. I will sketch out how to solve these kind of things. I'm not inclined to solve now because we should move and see other sections. They give you a flower garden. Now I'll tell you immediately two more applications. So this is 1 meter, 1 meter, 2 meters, 2 meters. And they say rectangular flower garden, the area of 30 meters squared is surrounded by a grass border 1 meter wide to the sides and 2 meter wide. The other two sides, what dimensions of the garden minimize the combined area of the garden and borders? So you have set 30 meters squared here, but you want to minimize, if I call this x and a y, you want to minimize x times y, which is the area of the whole thing. There are two modifications on this problem. One modification was a pool with a patio around the pool. So they tell you that the pool is of the area so and so, and you want to put a brick patio around. And then again, right, what are the dimensions so that the area is the minimum, so you buy less bricks, so it's less cost and less everything, right? You can spin it in any way you want. And another one was publishing of textbooks or books in general, because you give area for the printed text, which would be like 30 meters squared. Well, we're talking now inches. So you give the printed, so take this picture in your head and flip it, right? Landscape, portrait. And the text would be in here, which is the area that is kind of standard. And then the margins would be this 1 meter and 2 meter, in your case 1 inch, 2 inch, to minimize the size of the paper, right? Because less paper, less cost. So, you know, there are a few variations for this problem. Now you see that you are supposed to minimize x times y. Just the trick is how to come up with the inner equation. So, what is the equation for 30? What are the sides that are multiplying? Beautiful. Beautiful. Yep. So when you look at the picture, you see that if this is x, then this side over here is x minus 4, because you have 2 taken from each side. So the inner, which we'll call inner a times b, right? So a is x minus 4, and b is y minus 2. So you have this now, you solve for either x or y, and then plug in the other take derivative and you're done. So variety of those problems around, whether it's flower garden or a pool or book. If you have a Larson book, right, it will be a textbook problem with margins in the same area. So a whole bunch of cool problems to work on, and you know, work as many as you can, and then stop by, ask questions if you have any. That's it. So we're gonna stop the stream on this one now. Say bye to the stream and restart with next lecture.